Good morning, guys. Welcome once again. This is our condensed matter physics lecture series. We are at the ninth lecture of superconductivity, and today we are on the last topic of superconductivity. That is, name is the flux quantizations. In some previous lecture, we are discussing about the different kinds of theory which is related with the superconductivity, like the London's equations, and after that the London theory. After that, that is BCS theory, which helps to know the characteristics of superconductivity in a different manner. And later when we are of the Cooper pair, we discussing such kinds of different aspects related with the superconductivity. Now we are on the flux quantizations. It is the last topic related with the superconductivity. Now in that, the flux quantizations which is related with the superconductivity firstly is introduced in the 1950. The first introduced in 1950 by the scientist of the Ginsbury and Landau. These two scientists, with the help of wave functions, with the help of complex wave function, they describe the superconductivity state. Now let us start these, find out what is the flux quantizations in the superconductivity. Firstly, we assume the density of density of superconducting electron, density of superconducting electron, and the density of superconducting electron is nothing but the ns is directly proportional to wave functions square. Now let us put the equation number 1. For these equations. Okay. Now the psi, it is called as the complex wave functions, and this psi will considered as we considered as an order parameter, and these order parameter describe the superconductivity. This order parameter describe the superconducting state. Okay, now I think it is very easy for understanding superconductings. Now for the given function, at psi, for the given functions of psi, the position in material is not constant. For given temperature, what I say, for a given temperature, the psi, which is the function of position in material, it is not constant. It is the one kind of the criteria which is using the wave function psi, and this psi is vanishes above the critical temperature. This psi is vanishes above the critical temperatures. Now the wave function psi, the wave function psi can be written, these wave function psi can be written in term of magnitude and phase, that is psi is equal to mod of psi exponential of I into phi, that is called as the equation 2. That is equation 2. This is equations related with the magnitude and phase in term of wave functions, and the current density is nothing but the J is equal to minus of twice E square divided by MC into A plus EH cross divided by M into del phi into mod of psi square. Let the equation number 3. We have the 3 equations is here. First equations we shows the density of superconducting electrons. That means those electrons are known as the super electrons, that of the density of that equations. Second one, equations which is related in terms of wave functions and which shows the magnitude and the phase, and third one, equations shows the current density. Third one first says shows the current density. Now let us consider the one kind of the superconducting material. Now let us consider a superconducting material which is in a shape of a ring, that is ring, and the figure is like this one, look like this figure. Okay, just I copy this figure here. Look in that figure. We see in that figure the ring like shape was here, and these are one kind of the closed loop. These are like one like of the closed loop. So let us see with the help of these closed loop, that is integration over that closed loop J into dl is equal to mod of psi square into phi in bracket twice E square upon MC into A plus plus EH cross square divided by M into del phi bracket close into dl, and this is equal to 0. Now put the equation number 4. Now when we see these equations, after that we can easily understand with the help of Stokes theorem. We can easily change these equations. What happens in the Stokes theorem? The integration J into dl is nothing but the integration into divergence of A into ds. It is a vector A, and this is nothing but in term of magnitude it is B into ds, and whole this is equal to phi, and put the equation number 5. This phi is called as the flux. And this flux is enclosed by the ring. And look at the diagram. This is the flux, and this flux is enclosed inside that ring, and which are shows by here the phi. Now in order parameter, the single valued, and the phase change around a closed path. The phase change around this closed path. The phase change around this closed path must be 0. This must be 0, or which is integral multiple of 2 pi, which is integral multiple of 2 pi. Now with the help of this base we show, that is the del into phi dl is equal to 2 pi n, equation number 6, and this n is the integer. This n is the integers. Now look at the equation number 6, look at the equation number 5, this one, and look at the equation number 3. Now all these equations shows the one kind of the magnetic flux, which shows the magnetic flux, and this magnetic flux is enclosed by a ring. This flux shows the this is the enclosed by the ring, and this must be quantized. This must be quantized on the basis of equation number 3, equation number 5, and equation number 6. We can easily write phi is equal to NHC divided by twice E, and it is nothing but the N phi 0. It is nothing but the N phi 0, and this is the equation number 7. This is the equation number 7. And what is the phi? Phi it is nothing but the HC upon twice E. That is phi 0. That is phi 0, which is considered as here. We can just here where phi 0 H is nothing but the HC divided by twice E, and the value of this factor is nothing but the 2.07 into 10 to the power minus 7, and unit is Gauss centimeter square. The value of this phi square is 2.07 into 10 to the power minus 17, and this equation is known as the fluxoid. This equation is known as a fluxoid, means this is also called as the flux quantization. This is known as the flux quantization, or it is called as the flux quantum, not the flux quantization, called as the flux quantum. Now we have the another one equations which is related with the flux, that is equation number 2. Where is the equation number 2? This equation number 2. This equation number 2 says that the flux they shows you equation number 2 does not hold flux penetrates in the ring itself. This equation shows you the flux penetrates are not be hold in that ring. That means it is a continuously outward. It is continuously outward. With the help of this equation, we can easily write phi is equal to phi external plus phi SC, that is called as the superconducting. So this phi or these equations is called as the flux quantization. This is called as the flux quantization. Now it is all about the flux quantizations. So guys, just revise this again once again. What is the flux quantizations, or what is the equations of flux quantizations? Firstly in the 1950, the Ginsbury and Landau introduced the complex wave function psi, which describe the superconductivity, or which shows the superconducting state. And after that easily we get the detailed criteria about the flux quantizations. What happens in that? We used basically three different equations. The first one equations which is used for the density of a superconducting material. The equation for superconducting material is nothing but the ns is directly proportional to mod of psi square, and we put the equation number first for this one. And second equation, it is another in term of wave function, complex wave function psi. This psi can be written in term of magnitude, and phase is nothing but the psi is equal to mod of psi into exponential of I into phi. This phi, it is related with the flux. This phi is related with the flux. And we need another one equation. We need the another one equations. The equations like the current density. And what is the equation for current density? The equation for current density is J is equal to minus of twice E square upon MC plus A plus E H cross M into del, or diversion of phi into mod of psi square. In the equation 2 and 3 we see the term of flux was introduced. Look at the equation number 2 and 3. In that, this phi, and equation 3 this phi, this is introduced for the flux. This is introduced for the flux. After that we consider a one ring which is made by a superconducting material, and taking the closed path of this, taking the closed path for this ring is nothing but the integration over the closed loop J into dl is equal to mod of psi square in bracket twice E square upon MC into A plus E H cross by M into del phi into dl, and this is nothing but the 0. This is nothing but the 0. Why? Because phase change around closed path must be 0. Closed path, when we consider the closed path, the phase change around this closed path is 0. So after that, the integral is a multiple of 2 pi. Integral is multiple of 2 pi. And another one thing was here, we use the Stokes theorem for the purpose of change the volume integral to the line integral or vice versa. So after that, from the equation number 3, 5 and 6, the magnetic flux which is enclosed by the ring is must be quantized. So phi is equal to NHC upon twice E is equal to N phi 0 is equal to N phi 0. Now the name is equation number 7. That is the equation number 7. So in that equations, these phi 0 which is used for the NH upon twice E, NH upon twice E, and what is the value of equation for the HC upon twice E, and the value of this equation HC upon twice E is the 2.07 into 10 to the power minus 7 Gauss centimeter square, and is known as the fluxoid, or it is simply called as the flux quantum. Now we have the equation number 2, which shows the magnitude and phase of our flux, which shows the magnitude and phase in terms of the complex wave function, and this shows another one thing, That is, the flux cannot be hold in the ring. The flux cannot be hold in that ring. So the equation phi must be phi is equal to phi external plus phi SC, that is nothing but the superconducting factors, and this phi is known as the flux quantized. So I think this lecture are understood very well. If you have any query related with this lecture, please ask me. And guys, another one thing, here the superconducting factor was over. From the next series, next lecture series, we goes with the magnetism. So guys, thank you so much and enjoy your day.